Hello everyone, I hope you enjoyed that video. So that was the superposition of quantum states. So you see that what we see is pretty much because we can't isolate a quantum system, what we see is actually one of the two states that's being displayed. So when we take so the like for particles, quantum particles, they exhibit this kind of superposition of quantum states. They could be in one state or another state. So, and we usually characterize that as a non-excited state or an excited state, where the excited state eventually they go back to the other state and they emit a photon of light, and that's kind of the light. Sometimes we see, so like all matter can kind of emit this kind of light, and that's kind of what gives our world a reality that we know and enjoy. Okay, so let's continue where we left off. Now, part 2 of quantum mechanics. Okay, so I wanted to go over again this kind of looking at the kind of using the spectroscope here, talking more about the line spectra of atoms. Okay, so if we use a spectroscope, we point at the light source, and then there's going to be a if we point the light source on a slit, we're going to actually see a diffraction pattern, and that's going to produce some colors here. Okay, and then on the spectroscope, there's a actually diffraction pattern where the light will show up, and then these bands of light will show up here, and we can actually decipher the colors of light within our source. Okay, so in this case, this would be green. So let's just mark it with a green color just to be fun here. Green. Okay. This one would be blue. And this one would be violet. So I do have a violet color, I think. Yeah, here we go. You see here, they appear at characteristic wavelengths. So our source of light, we can separate into colors that represent, different energy levels for that source. So it could be a source of, some atoms or another material. It gives us insight into what these electrons are doing. Okay. So let's go back now to this diagram here and talk about let's talk about the energy levels. So we saw that kind of very fine diagram with all those lines, but now let's go into more detail. Okay. So this transition from the lowest level n equals 1 to n equals 2, this is called the first excited state. Okay. So what electrons can do is actually travel between these energy levels quite freely, and but to do that they need some energy, right? And usually to see the population of these states, we need to actually supply the energy in the source of electric radiation. So our world is filled with electromagnetic radiation, right? So we can actually, an experiment, what we would do, we would shine light on a material, and this would give us a method of observing these excited states or these transitions. So that'll be the first excited state, and then when we go to the second excited state, we will represent this transition from the ground state, n equals 1, to the second excited state, which is n equals 3. So this is called the second excited state. Okay, and n equals 1, we call this the ground state. So let's kind of abbreviate that here. Ground. Oops. Okay, so the ground state is what we call the lowest energy level. So that video was kind of trippy a little bit because what we do see is that the superposition of these two states, they're now gone, because usually in reality these molecules or particles are interacting with things around it. And when they collide, it's going to cause them to only exist in one state or the other, because you kind of disturb the equilibrium of the two states. So what we actually see when a photon of light hits the particle, we see it in the excited state. But in reality, these states can coexist, and that's what we call superposition. So I think that was a pretty fascinating video. But it kind of helps to understand what we're doing here is that for an electron to access the other quantum state, it has to absorb energy. So we can kind of, what we call, like in the video, it's called decoherence, where we kind of separate the boundary between the two states. So now we can see or, establish a boundary between the two states. So now we can observe them separated and view them individually. So usually we say that, okay, electron is either in an excited state or in the ground state. So it's going to be in an excited state, which has many excited states, and then or it can be in a resting state or a ground state or lower energy level, to put it simply. Okay, so we say the ground state is also the most stable. Okay, the most stable energy state. And it's it's closer to the nucleus, so closest to the nucleus. Okay. All right. So we call this big graph right here. This is called the energy well. So basically, it tells us the energy of our particle, or in our case, the energy of the electron. So we call this the energy well. Okay. And the farther down we go, the closer it is to the ground state, more stable, because you have lesser energy. So these negative values tells us that the electron has less energy because it's moving closer to the nucleus, so it's going to have less energy to like kind of move on its own. All right. Okay. So, and then we say closer to the top. Okay, that's going to be less stable because now the electron has more potential energy to move freely. Okay? All right. And you see here that between these lines, we can have several different transitions like we saw in the other diagram in the last lecture. We can have all these different kinds of transitions here, like so. So it could be like this, or it can also, we can have several different transitions, okay? Like so, 5 to 4, or 6 to 5, or 6 to 4. Or we can also have, 4 to 2. So there are several different transitions that we can have, okay? So what we want to say is that there are many we call these electronic transitions because electrons are jumping between energy levels. There are many transitions. So this topic is a pretty tricky one because it's really delving into things we usually don't talk about, and it's more on the physics side of things, but we do teach it because it has to deal with the electron. Okay. So what can we say about the energy levels? Well, the energy levels, okay, are quantized. Well, this means that there are specific values of energy that the electron can have. That the electron, oops, sorry, that's a little messy. Electron can have, okay? So electrons can populate different energy levels by having this amount of energy. And like we saw in that kind of animation there, once the electron or particle absorb enough radiation, it can actually get to the excited state and then fall back down. So it can occupy either of those states. Okay? So that's how we think about the energy levels for atomic hydrogen here. Okay, so let's answer these questions. Maybe it'll make things a little more clear here. All right. An electron in a more stable state is also described as being in a lower energy state or a lower energy orbital. So an electron in which n level is more stable So which one is more stable? N equals 5 or N equals 3? Let's explain our answer. Okay. So remember, the higher the energy level, the more unstable it is. So an electron in the N equals 3 level is more stable. Is more stable. That's actually backtrack a bit. So it's closer to the nucleus than an electron. In the N equals 5 level. And that's because the protons are an attractive force. It's positively charged and is an attractive force, so it'll stabilize the electron if it's closer by. Therefore, it will be more stable. Okay. So if we think about the force of attraction between two objects, the force equals Q1 times Q2. Well, it's not capital Q. Q can also mean charge in this case. So let's do Q1 times Q2 over the radius between the two charges squared, or the distance between two charges squared. So in this case, Q equals charge on an object and R equals the distance between the center of both objects. So pretty much is the distance of their radii from each other. Okay, now let's try this other question. Which N level should the electron hydrogen occupy to be in its most stable, lowest energy state? And why is that? Okay. So if we think about the energies in our diagram here are increasing as we move further away from the bottom of the well. So that means it has more energy. And if the electron has more energy, it's going to have more kinetic energy and also more potential energy as it moves away from the nucleus. So what we can say is that the most stable state should be the state in which it has the lowest energy, or where it's closest to the nucleus, and it has the it's in the bottom of this well here. So we're going to say energy levels start at the N equals 1 level. Okay? An electron in the hydrogen atom should occupy the most stable energy level. Which is the n equal, which is the n equal 1 level, because it has the lowest energy. It has lowest energy. So stable just means, you know, in chemistry, it pretty much means it's a system, or in this case, a particle that has the lowest energy. So it doesn't want to, you know, it doesn't have energy to give away. It doesn't have energy, you know, to go do something else. So stable pretty much means you are of lower energy and you have the lowest possible total energy that you can have at any given time. Okay? So in this case, electrons in the ground state, that's the lowest energy level. So there'll be the electrons in the ground state. They tend to be the most stable electrons, and they're the least likely to, you know, kind of participate in a chemical event. So usually electrons in higher energies are the ones that kind of react first, and that's why when we do chemical reactions, we only talk about the valence electrons because they are in higher energy levels. But we'll get more into that when we talk about electron configurations. Okay. All right, so let's stop here, and then we'll talk about the terms low energy and high energy as part of our next exercise. Okay, so I'll see everyone then. See you in the next video.